So this is from Cutnell and Johnson's Essentials of Physics textbook, and this is chapter 20, electric circuits. So I'm going to analyze a small number of circuits, combination, parallel and series. And I'm trying to get ready here. I almost started this recording by accidentally having turned off the microphone. So that would have been a bummer. I'd talk all this time and then nothing would have been recorded. Anyway, here's the first problem I want to talk about. Problem 58. It says, find the equivalent resistance between points A and B in the drawing, and you can see the resistors here. So to analyze that is to figure out which ones are in parallel and which ones are in series. In fact, which ones are purely in parallel and which ones are purely in series. The way to look at that is to see where the junctions are, and there you have to be careful. Hey, what's happening here? For example, here's something not to do. Are 4 and 3 in parallel? No, they're not purely in parallel. It kind of looks like it, but they're not, because there's the 6 ohm resistor here, which is between these two junctions here. So that throws it off. Are 6 ohms and 1 ohms in series? No, because there's a junction in between, so that can't be. So where do we start? Well, actually, it turns out there's a very easy part where we can see it where to start, and it's these 3 resistors, which are definitely in series with each other. Don't pay attention to that there is a bend in the drawing here. They're still in series with each other. So purely in series, which is 1 plus 2 plus 3, which is 6 ohms. So the solution, which is already posted here, takes these 3 here and puts them in series, and there's the 6 ohms. So what we did is we reduced this entire circuit here by taking the last 3 resistors, them being in series, means we have a 6 ohm resistor here, and we have redrawn this. All right, now how do we continue? Well, again, look at where the junctions are and figure out if something is purely in series or parallel. Turns out it's still on the right hand side over here, where these are definitely in parallel with each other. We have the junction here. This is actually this one right here, and this one right here is the same junction now, actually. And there's nothing in between. Hence, the 2 are definitely in parallel. The same thing at the bottom, by the way. So we have 1/3 plus 1/6. We add those 2 fractions here, and then we take the inverse of that, and apparently if you do that, you come up with 1/2. In fact, if you cut a pizza into thirds, and then you take another 6 there, you actually do come up with half a pizza. So that's the 2 here. So the 3 and the 6 here therefore combine in parallel to the 2 right here. So this one is being substituted for this whole thing. So here we go, and I think you can see it that these are definitely now purely in series with each other. So it's 6 plus 2, which is of course what we have here. So we substitute the 8 here for the 6 plus 2, draw it in here, and again purely in parallel, these 2 here, so 4 and 8, which means 1/4 plus 1/8 right here, and then take the inverse of that once you have that on your calculator. That's kind of like 0.25 plus 0.125, which is 0.375. I'm doing that in my head, by the way. And you take the reciprocal of that, and you come up with 2.67. So again, this one is being substituted for these 2 here, and then at the end it's these 2 here being purely in series, which means that the result is going to come out to 2 plus 2.67, which is 4.67 ohms. I'm going to take a little pause here. That was actually just a few seconds of a pause, just wanted to catch my breath. And I prepared this one here in the Physics Education Technology applet. And so I'm going to do that in just a moment. So just keep this one in mind here. This is the circuit 2, 6, 1, 4, 3, 2, and 3. and that the result is 4.67. So here we go. So there's the 261, 432, 3. Now remember that the result is 4.67 when I'm all done with this one here. The thing is, once I close the switch here, yes, we have a current flowing here. The PHET circuit does not allow me to measure resistances directly, so I cannot measure the total resistance. So I'm using a little trick, Ohm's law. I adjusted the battery voltage in such a way, notice 4.7 is a little bit unusual, 4.7 volts, so that the current, this is the total current that flows through here, is a nice 1.01. I cannot make it any closer to 1.00. That's it, actually. And if you divide by 4.7 by 1.01, Ohm's law, yes, you do come up with, well, just a little bit less than 4.7, which is the 4.67 that we have as the result. So that's what I'm aiming for here. This is already the total resistance. And now what I'm going to do is, just like I did in the analysis, I'm going to substitute these resistances here. So this one over here, oh, before I start, actually notice that for some reason the switch is highlighted here. It has 0 ohms. It shows the values here. So right now with the switch open, it says infinitely many ohms. So there is no current, obviously. Close the switch. Now it has 0 ohms. That's fine. That's fine. Just leave it like that. Kind of ignore this one here. So anyway, I start over here, 1, 2, and 3. I add them all, which is 6. Okay, and I'm going to substitute that. So here's what I'm going to do. I'm going to, let's see, take this one out, take this one out, change this one. It's a little bit off the screen when I change that. There we go, 6, reconnect, and notice the current down here. There we go, back to 1.01, which again, 4.7 divided by 1.01 is that 4.67. By the way, if you do that 4.7 divided by 1.01, it's 4.65, but this is restricted with its significant figures. I cannot do it any more accurate than what the software allows me to do. All right, so now I have these two here in parallel, 3 and 6, and the analysis showed earlier it ought to be 2 when I substitute that. So I'm going to take this one out, this one out, this one out, and change this one here to 2 ohms. Takes me a little while there. Doesn't let me type, so I have to use a slider. And again, I still am back to 4.7 divided by 1.01, 4.67. Okay, these two in series with each other. I just want to double check. Did we have an 8 there earlier? Oh, we did. Yeah, we did. So these two here in series with each other is indeed 8. So I'm going to take this one out, reconnect here, and there we go, 8, and I'm back to 4.67. 4 and 8 in parallel with each other is 2.67 as the analysis showed us. So I'm going to take this one out, and I'm going to change this one here to 2.67. Okay, close enough. I cannot get it any better. So 2.7, and 4.7 divided by 1.00 is the 4.7 is still the result. And of course, when by the way, I left these wires in here. Well, they are not connected. It's not a closed circuit back here, so it really doesn't matter if they're there or not. But if you really want me to, I will take them out. There we go. And then these two here added 2 plus 2.7 obviously is 4.7. So I'm going to change that one here, last one. And of course, we're done. Same analysis with a simulated circuit. All right, I took a little break here accidentally. Instead of pausing, I stopped, so it's okay. So next recording that I'm going to then later put together, and I have to find where my Word document is. There it is. All right, so I'm going to scroll down to the next problem. So for the combination of resistors shown in a drawing, determine the equivalent resistance between points A and B. and again purely parallel, purely series, so obviously 65 and 85 are such, so I have to add the reciprocals, and I'm going to pause because I wanted to open my online calculator, so I'm going to shift this over a little bit, and maybe I'm able to squeeze it in there. There we go, that might work. Old formula, I forgot what that is. Looks like a complicated physics forces problem or something. Anyway, I don't need this. So 1 over 65 plus 1 over 85. There we go. Enter, and then take the reciprocal again. There we go. 36.8, which is what it says. Well, they rounded to 37, so that's fine. And then I take the 36.8 and I add the 63 to it. So 99.8, but it is two significant figures, so this one is 100 ohms. And yes, we have an ambiguous case, right? The first zero actually is significant because it's too significant, and the last one is simply a placeholder. And yes, they indicate that here with the scientific notation, but writing 100, I don't think it's necessary to use scientific notation, even though the answer, writing it down 100 ohms, again, would be a little bit ambiguous. But we know it from the context. It ought to be too significant. In any case, it's 100 ohms. All right, let's see. Next problem. Okay, that one actually I'm not going to do. Coffee maker and frying pan. So here we have another complicated one. And I'm going to take a pause, prep this one. All right, it's a good thing that I prepped it because this one actually doesn't have these diagrams there where they keep substituting, so we have to kind of do it in our heads without the visuals, but we have this visual here. So here again, what's purely in parallel, what's purely in series, and I think you can see that these two are definitely purely in parallel, and if you can also see it, these two here are purely in series with each other. So we have a 10 ohm over here, right, 4 plus 6, and we have a 9 and the 8 here, which are purely in parallel. So I'm gonna do these here first, 4 plus 6, because it's so straightforward. Obviously, 4 plus 6 equals 10. So that's the 2 in series. Now I'm gonna have 9 and 8 in parallel. So I'm gonna do this. This is a quick way of doing it. 9 to the negative 1, which of course is 1 over 9, plus 8 to the negative 1, and yes, it is 8.0, but the calculator actually doesn't care about sig fig. Parentheses, and now I take the reciprocal of it again, like this. There we go. And then enter. There we go, 4.23. So these two here are 4.23, and now these two here are purely in parallel with this one. So I'm going to take the answer here. It's a quick way to do it, and do it to the negative 1 power, so inverted, reciprocal, plus the 10 from these two here to negative 1, close the parentheses, and again take the reciprocal. There we go. And I come up with a total of 2.97. By the way, if I had recognized that as these two here are in series with each other, 4 plus 6 is 10, and then on top of it, they're actually purely in parallel with the two others here as well. So 9, 8, and 10. Watch this. There we go. I can squeeze the 10 in here. So plus 10 to the negative 1. Close the parentheses right there. And I come up with the same thing, 2.97. But, you know, if you don't recognize that in one step, you know, then just chop it up into smaller steps. Okay, so 4 plus 6 is 10, and then the 9 and the 8 in parallel with each other is 4.23, and then both of them are in parallel with the 10 here. So do that again, 2.97. Now that 2.97 overall here is in series with the 3. So add 3.0, 5.97. Now that means that all of this stuff over here is going to be in parallel with the 20. So I'm going to do this, parentheses, answer to -1, the reciprocal, plus 20, this one, parentheses, and take the reciprocal again. So what I have here is 20 and 5.97 in parallel with each other. Now in a parallel part of the circuit, the equivalent resistance is smaller than the smallest resistance, so it ought to be less than 5.97. Here's a little other hint, I know that from experience, that if the other one that's in parallel is actually relatively large, then the result is not that much smaller than 5.97. So I'm guessing 5 or 4.5. Let's see what happens. And there, in fact, there it is, 4.6, which is exactly what they have here in the solution. And of course, the description that they have here is the same thing that I just did on the calculator. And I figure I'm also going to do that with the FET circuit. Remember that the result should be 4.6 when I'm all done. So here it is, but I'm going to take a pause from recording so that I can actually assemble that. And you know what? 4.6, by the way. I still have the switch here, and oh yeah, I do need a resistor here, so you can see, you know, this is actually how it's being built. And then let's see, this one is actually the 20 ohm resistor. There we go. And then I'm going to put a resistor over here, and then I'm going to connect over here to the next one, and then to the next one over here, and so on. And I'm going to take a break, and then when I return, you will see that this one is finished. All right, almost finished here, just a couple of wires, and I still actually have to double check that I did this correctly. How much should we come up with? 4.6, right? Okay, I have to, oh yeah, this one here. This one should be a 3. There we go. There we go. Look at this. 4.6 divided by 1, according to Ohm's law, is actually the total equivalent 4.6 that we should come up with. Okay, so again, here's the analysis. So 4 plus 6 is 10. So I'm going to change this one here to a 10 as I combine these two in series here, which means I no longer need this one. There we go. Back to 4.6. 10, 8, and 9 are in parallel, and if I'm not mistaken, that came out to 2.97, which is going to be 3. So I'm going to substitute all of this here just with one resistor, which I will call 3, and I take the others out. So this one is gone, this one is gone, the wires back here don't matter at all, and I'm back to 4.6 divided by 1 is 4.6. Okay, 3 plus 3 here is 6, so I'm going to get rid of this one here and change this one to 6 ohms. There we go. Reconnect the wire over here. 4.6 divided by 1. There's the 4.6. Okay, and yeah, now I really don't need these wires here. There we go. There we go. And then 20 and 6 in parallel with each other. That actually then came out to the 4.6. So let's see. There, take this one out, and obviously, yeah, 4.6. All right, so next problem here. Oh, yeah, this is the one we just did, so I'm going to scroll down. This one I'm actually going to skip. The solution is still there. Didn't want to take it out. Okay, so this one I want to do. So this one says, the circuit in the drawing contains 5 identical resistors. Whoa, what happened? The 45-volt battery delivers 58 watts of power to the circuit. What is the resistance of each resistor? Okay, the way to start with this one here is, I'm going to type this on here, hopefully. Power equals voltage times current. Ooh, nice looking I like that. Actually, I do like that I. Notice that none of this here is actually the resistance. However, when I use Ohm's law, current equals voltage over resistance, and now I'm going to combine these two. So I'm going to have power equals voltage squared divided by resistance. And as you know, as I'm typing, it's always a little cumbersome. And which is exactly what they're saying here in, and with they is actually the people who did the solution manual. What they're saying here, power equals voltage squared over the equivalent resistance. So I'm going to put an EQ there, which is the total. And so what we have to figure out is, well, what is the equivalent resistance? And from that, we can figure out what the individual resistances are. Let me actually do this one here really quickly, what the equivalent resistance is, because I think it's right in front of me. I just have to find my calculator. There we go. So clear this one here. So looking at the algebra, that also means that the equivalent resistance is voltage squared over power. Let me rewrite this one here. Hold on, and if I was able to write this here rather than typing, this would actually go quicker. There we go. There we go. I got it. Voltage squared over power is the equivalent resistance. Now I'm going to use the calculator, which is going to be 45 squared divided by 58, and that's the total equivalent resistance, 34.9, roughly 35. Let's see if that's actually true. They say that somewhere. Ooh, actually, they never said that. 35. But in any case, that's what it is. Now I have to figure out what the individual resistances are, and with them not being given, well, it's going to be kind of interesting. The thing is, they're all the same. That's what it says here. 5 identical resistors. So it doesn't even have to be labeled R1, 2, 3, 4, 5. They could be all called R, but they did that. They labeled them individually here because then you can look at the analysis. And when you look at the analysis, you can say, okay, R3 and R4 are definitely in series with each other. So you write it down like that. And then R2 and these two here and the R5 are definitely in parallel with each other. And then when you're done with that, then this whole shebang here is in series with this one. So here's the analysis that they did. As I scroll down here, I hope we're not going to lose track of the drawing. Might have to do something there. Let's see, Control X. Ooh, the drawing is gone. There it is. All right. So what they do is here they put the R3 plus R4. In fact, let's see, right there, R3 plus R4. And now they're going to say, okay, this one, then these two here, which are in series, and this one here are all in parallel with each other. And that's what they write down here, from here to here. R2, R3, 4, R5, all reciprocals, realizing that the individual ones are all R, and that the R3, 4 is actually 2R, obviously. So again, each one of them is the same. So that's why you will see this one right here, 1 over R plus 1 over 2R, that's the one in the middle there, plus 1 over R. And if you do that with the least common denominator, which is 2R apparently, you come up with here 2 plus 1 plus 2, which is 5. So 5, 2 over R. So the combination in the back here is that 5 over 2R, but you have to take the reciprocal of that again. So these last 4 resistors here, they're actually 2R divided by 5, and you see that right here. 2R divided by 5, which is being added because these here are purely now in series with this one. So these two R over 5 are added to that R in the front there, and again, least common denominator, which apparently is 5, So we're going to have 5 plus 2, which is 7, 7R over 5. Okay. Let's see. I did say that the total resistance, which they didn't calculate, is about 35. So this one here actually would be the total resistance. So if I divide that by, hold on, I take that back. If I divide that by 7 and multiply by 5, I should come up with the right answer. 24.9 or 25 ohms rounded. Let's see if that's true. And indeed, there it is. There's the 25 ohms. All right, I took a little break here in order to set this up in PHET. So the resistances are all 25 ohms. My battery voltage is 45 volts. So let's go over here. And I'm almost done. There's the 45 volts here, and then I have 25 ohms, 25 ohms, and a couple more resistors to set up back here. There we go, and this one here, and this is always quite a bit of work, you know, just to prepare this one here. And again, I don't actually have a number that I can plug in there, but I have this little cumbersome slider here. I'm going to close the switch here. I'm going to have the total current here is 1.29 amps, and now I'm going to get to the calculator here, and I'm going to do 45 divided by 1.29 amps. This is Ohm's law. There's that 35 ohms that I showed earlier. You know, 45 squared. Oh, it's actually still towards the top there. That is the 35 ohms I had earlier. And the total power, of course, is when I multiply 45 times the current, 1.29, I come up with the total power. When I divide the two, then that's Ohm's law, I come up with the total resistance. So there we go. And there is that original 58 watts that was given. All right, and the last one that I wanted to do here. So determine the power dissipated in each of the resistors in the drawing. Notice that all three of them are 576 ohms. In order to do that, first determine the equivalent resistance. From that, then determine via Ohm's law the total current, and then from that compute the individual powers here. So purely in parallel, these two, 576, 576, and notice this is not a coincidence that this comes out to 288 when they're in parallel, but basically when you add these here, you already have the same least common denominator, so 1 plus 1 is 2, and then 2 divided into 576 when I do the reciprocal again, of course, is 288. So if you have identical resistors in parallel, for example 3 or 4, then you would divide by 3 or 4 in order to get the equivalent resistance as they're in parallel. So 288 ohms between these two here. Then these two here are in series with the 576, hence add the two. 576 plus 288 is 864 ohms. Divide the 864 ohms into the 120 volts, Ohm's law, 0.139 amps. Okay, so for the, and then you have to do kind of like 3 calculations. 0.13 amps multiplied with the first resistance, because this one is going to get the total current of 0.139 amps. So 0.139 amps times, hold on. One moment. I have to think about this for just a moment. Okay, I was going to multiply that with the voltage on this one here, but I don't know that actually because the voltage splits up in this circuit. So they suggest a different way of doing it, which is I have the 0.139 amps flowing through here, and then use a different version of the power law. Here it is. It starts out with power equals voltage times resistance, but then you substitute for the unknown voltage on that resistor Ohm's law, so voltage equals current times resistance. So maybe I misspoke half a minute ago. Power equals, let's see, I should actually write this down here. Let me write this down. So power equals voltage times current. That's what I meant to say earlier. And then I substitute Ohm's law for the voltage. So voltage is current times resistance times the current that's already there. Hence, you see that in the next line, current squared times the resistance. And I do know the current, it's the 0.139 amps that was just determined, times the 576, that's the 11.1 watts. Then, at the junction here, it splits up the 0.139 amps, so we get virtually 0.7 going this way and 0.7 going this way. It's a little bit less. Well, they simply wrote half of that 0.139. And because this one here is squared and then multiplied by the 576, that's why the 2.78 is about 1/4, or exactly actually 1/4 of the 11.1 for these here. So the identical resistors that are here in parallel with this one here being in series, they get only 1/4 of the power because they are in series with this one here. The current goes in with the square. All right, gonna pause, respectively stop, because this was the last problem I wanted to do.